Okay, so when we're looking at anything that's moving in a circle or has that circular path, that means that object will have a centripetal acceleration that is towards the center of the circle. And that means that there's a force that's actually supplying that acceleration. That's what we call the centripetal force. And we've been talking about and doing problems with things that have centripetal force towards the center of the circle. You really got to think of the centripetal force as the F net of the forces that would act in order to keep the object moving in the circle. So when it comes to our free body diagrams and our F net expressions where we're applying Newton's second law, we substitute Fc in for F net because we're going to use centripetal acceleration instead of regular linear acceleration. So in order, we know this, in order for an object to remain in a circular path, a force is necessary to cause the centripetal acceleration. For satellites, that's Fg. For a yo-yo, it's Ft from the string, for the most part, and at some points, obviously, the Fg will add to that, or subtract from that. On a non-banked curve between the tires and the road, we would have the force of friction supplying the centripetal force that would keep the car moving in that circle. But there can be a situation where no friction exists, or it's pretty much negligible. Like it's not a big enough force that would actually have an effect. In those situations, that means that the coefficient of friction between the two surfaces is pretty much minimal. And we have to do something about it to allow for this. And this is something that is really important when architects and civil engineers are designing roads and figuring out what kind of banking needs to happen, because we've got to keep cars on the road safely even when the coefficient of friction is so low that it's kind of approaching zero, which actually weakens the frictional force that would normally keep the car on the road. So if there's no friction, we're going to bank the car. We're going to bank the curve and lift the road up so that we can have something else that's actually going to supply the centripetal force and keep the car on the road, prevent it from sliding. And obviously you can imagine that's going to have some important effects, because then the object is really safe and not going to have some bad collisions or anything like that. So for cars going around a curve, what we've got going on over here, we've got this would be your velocity, what's happening there, that tangential instantaneous velocity that happens as a car is moving in a circle. Let's say they are, to me, this looks like they're moving clockwise. And then there is a force into the center. And that on a flat surface, that would normally be the force of friction, if it were flat. If it's not flat, it's going to be something else. And that's what we're going to figure out right now. We're going to figure out what else that could possibly be. So by raising up the road, by banking it essentially, the car is given a centripetal force toward the center of the circular path. And that means that there has to be something that's causing it, right? There has to be something that's causing it. And the cause of that centripetal force, main concept here, the cause of that centripetal force is the horizontal component of the normal force. The horizontal component of the normal force is going to supply Fc in these situations. Okay? So let's take a look at what's happening here with these sketches. We've got two cars that are on a curve, and we really want to notice that towards the center of the circle is. This really matters, right? Where towards the center of the circle is actually happening. That matters because the big question that we usually get is, why are we resolving Fn? We usually resolve Fg, right? Because the whole point was we wanted to find the force that was actually causing the motion, which would have been the acceleration or the movement that's actually happening down the slope or up the slope. That's where FGH is actually involved. But in this case, we've got a normal force. Oops, that's not a very good straight line. There's our normal force. Just like you do before, the normal force is perpendicular to the surface, but we're looking for the force that's actually keeping the car along the path of the curve, which means there has to be a force going into the center of the circle because there's an acceleration towards the center of the circle. There has to be a force there. And that's going to come from resolving Fn. So before I even do that calculation, I'm going to okay, so if we've got this example where we're on an icy road and we're going to assume no friction, that's going to make it easier. We can still do these problems with friction, but that's going to get a little bit more complicated, but it's definitely doable because friction would be along the slope, right? It would be either preventing you from sliding down or sliding up. So it would be along the slope of the incline, and you'd have to resolve that vector as well because some of that component of friction, the component of horizontal friction, I didn't say that right. The horizontal component of friction would actually be contributing to the centripetal force along with the horizontal component of the normal force. So it's possible, and I think you've got a homework question like that, so make sure you definitely give it a try, but that would be your strategy, that you're going to have to resolve friction as well. The textbook actually gives a really good example of what that looks like, so don't be shy, take a look at that and make sure you follow that one through. Okay, so in this case, we're going to borrow some of the information we've already done. We know that our object is on a banked curve and will be FG down. Yep, that's supposed to be straight down. And then borrowing what I've already done on the other side, just because I'm going to save some time for us right now. I'm not going to re-resolve it just because you already saw that. Oops. We would have FNH there. All right, what information do we know? We know that we want the maximum speed. That's kind of cool. It kind of matters, right? Because if you're a civil engineer, you need to know what speed limit you can put on these banked curves. So that's really matters. Look, you're going to know so much. It's so exciting. We know that theta is 15 degrees and the radius of curvature is 65 meters. Awesome. So on the other sheet that we just did, we said that FNV equals FG, which is mg, and then we're going to say FNH equals FC. So in a question, if you're doing this on a test, you're going to actually have to validate, like have a nice resolved vector triangle that will actually show where your FNH came from. But since I just did that, I'm going to borrow what I've already previously done and apply it to the question that I'm doing. That's totally legit. You can say that FNH is mg tan theta. And our FC is mv squared over r. Watch this. This is going to be fun. M's cancel out. What do we want to find? We want to find V. To get V by itself, I'm going to have square root of, that sounded funny, square root of GR tan theta. I'm going to substitute those numbers in and see how I did. Let me bust out my calculator here. Oh yeah, times tan 15 and square root it. Bam, 13.1. Awesomeness. So that's the maximum speed that would be supplied by that centripetal force, which is caused by the horizontal component of the normal force. All right? Pretty straightforward, but make sure you give the practice a try because you're gonna wanna have some confidence of how to do these problems for sure, because you're definitely gonna get a banked curve question on your test. Okay? Thanks everybody. See you soon. Add another slide. Yes. I'm going to show you what this free body diagram should actually look like so you can make sure that you understand where everything is coming from. So if we have, let's say, that truck on the other page, there's our theta. Here's our block. Look at how similar it looks to our sliding friction issues. If we have the truck that's going on this banked curve, we would draw FG down. And then, wow, I really can't do that straight, can I? Erase that. And Fn that way. Again, perpendicular to the surface. Once again, we're looking for the object, the force that's causing the object to stay in the circular path. And you can tell that if you were to resolve Fg, you would end up with a force this way and a force this way, which would allow it to slide down that banked curve. And we don't want that to happen. We want a force that's going this way. So we got to be picky here. We got to actually resolve Fn. We're going to resolve Fn, and it's going to look like this. We're looking for something that's going to counter that force of gravity. Sorry, I'm trying to do that dotted, but it didn't work out very nicely with this stylus. Resolve Fn. Fn is made up of something that has gone, let me try and make this bigger. Oops. Nice that. Bear with me for a sec. Okay. Fn is made up of something that has a vertical component, there it is, and a horizontal component. That's no surprise. This is where your angle is. That's where theta is. So our angle actually goes in between FNV and FN, just like where I've placed it there. That's where our angle is going to go. And if that's unclear as to why, I can show you why later on. It might be easier to do in person versus over this way, but it might be obvious. So I can also kind of give you a chance for that. But you can see that if we redraw, come on back, there we go. Oh, it won't move as a whole object. Okay, fine. If we redraw that free body diagram, it's going to end up like this. Still on the slant, right? Because we want to show that it's a banked curve. FG down. FNV up. And then there's our ticket. FNH. That is going to be supplying the centripetal force in towards the center, and it'll keep this thing on the curve. So the cool thing is that we actually know that since Fg is equal to mg, we can also say that this would be Fnv would be mg, just in the opposite direction, right? It would just have an upwards vector, and you can see it. That's not supposed to be an, it's just supposed to be equal sign. Sorry about that. It's just mg in the other direction is where I'm going with that. Okay. So we can use that information to have help us out, because we know that when we're doing our calculations and say we want to find the force that's supplying the centripetal acceleration, or say you want to find the velocity that the car is moving at as it goes through this circle on a banked curve, we need to find, we would say FNV equals FG, and then you'd also be able to say FNH equals FC. Those are kind of like your Newton's first law statements. So just joking, Newton's second law statements that would actually go with this situation, right? So when we actually take a look at the triangle that's involved that makes up our, there's our FNV and our FNH. When we actually take a look at that triangle, there's theta. I'm going to mark this as HOA. We know that FNV is actually mg. So that's going to help, because I can actually put that in and say that FNV is actually mg. It's going to help us when we need to actually figure out what FNH is. In order to get FNH, I'm going to have to use the opposite and the adjacent side, because I know this side. Usually I know, I might know something about the hypotenuse, but I know the adjacent side this time. So I'm going to use my trig ratios, and I'm going to say the tan of theta would be equal to FNH over FNV. But that's exciting news. Wow, I don't know how to make this all, sorry, I'm not awesome in this app. Haha, just trying to figure it out. Sorry about that. That we can now say FNH over mg, because we can substitute FNV equals FG right down there. Okay, so now you end up with this relationship. Let me do it. You end up with an overall relationship where you can say that FNH H equals mg tan theta. Sweet. And then guess what you're doing? You're setting that equal to FC. So, ooh, fancy stuff. We can use that to help us find our centripetal force if that's what we need to do. Let's flip back to